from the Sunshine Coast, Queensland, but right now we're in Bali finishing off our holiday, which is pretty exciting. So some content that we'll be running through today is the overview of CAD, benefits of using CAD tools through the design process, and tips for beginners and engineering workflow integration. So to start off with, we're going to go over what is CAD. So CAD is standing for Computer Aided Design. So CAD uses a computer to aid in the engineering design process of creation, modification, analysis, optimization of a scalable robot concept. It is an industry skill and application. This can be used for FTC in the creation of the competition robot and parts and event handouts like key tags and 3D printed giveaways.
There are many CADs to choose from designing your robot. Just to name a few: Onshape, F360, Autodesk Inventor, and there are many good reasons to use these softwares. Just like Onshape, where it's very good for beginners. You can share and collaborate in it. It's also a browser website, and it's cloud-based. F360 is very simple. It can also share and collaborate. It is also only a cloud-based CADing software. It uses a variety of analyzing tools as well. Autodesk, on the other hand, it's more experienced, and to run it, you would need more experienced CAD designers. There are more advanced tools, but you're unable to collaborate and share on it.
Thank you, Dean. So our other member should be on and presenting this slide. Oh, Ellie, do you want to just go ahead? Sure. So our software selection, the software we use for CAD in our team is Onshape. This software is very suited for rookies. So myself, I learned this CAD software in 2 weeks and then shared it with the rest of the team. We also use our GoBuilder and Rev as well, and we use that to integrate into the software, which is really easy that we found to make our robot virtually. Then we could be able to create it in real life. The pros to Onshape is that it's easy and quick to learn. It's extremely collaborative, and you can also add comments and tasks to certain parts and assemblies within the design. However, you cannot render unless you buy a pro license, and unfortunately it is slower and more steps to simulate moving parts. For our robot this season, we opted for more simple and basically a robot that has less moving parts, which allows us to have a more accurate sort of robot. Now, when incorporating these sort of things and CADing it is a lot easier because we don't need to focus more on like where to put, say, a hole, and it's also easier to simulate a single, say, servo or motor and make it move a whole mechanism instead of having to CAD different servos and all sorts of movement points. Yeah, cool. Okay, so allowing for multiple design iterations. So CAD is really amazing in a sense. You can go through multiple iterations before you make it in real life. So for example, on the screen, we have some 3D printed hook designs we brainstormed in the early season. So we went through a lot of designs, some of which are demonstrated on the screen. And to save filament, we designed them in CAD. And then once we were happy with our design, we were able to print out the final one instead of printing all these different iterations and wasting filament. Just to add on, can we just go back a slide? Yep. So just to add on to that, when CADing, so we didn't have the 3D print out, we just extruded and made a, I think it was a 35 diameter, basically cylinder that was the diameter of the truss that we hung off. So that's how we know how to get the perfect diameter for our hook instead of printing it off every single time to make those fine adjustments. That's a great point, Lawrence. So collaboration in design iterations.
In most CADing softwares like Onshape, you're able to share documents like your main robot CAD with your whole team. You can create updates, and so pretty much your whole team is able to share through this, and everyone's able to make updates that you need to do. Even if someone's off on a holiday or something, you're still able to, the rest of the team's still able to access it. Next slide, please. The CADing software that our team decided to use, and we would suggest, is Onshape. Because since we're a rookie team, it really helps for us, because we're just getting into CAD. So for all the rookie teams and all the teams that aren't really into, haven't really started with CAD and all that, we would suggest using Onshape.
So showcasing the designs. Within the portfolio, you're able to use CAD to professionally communicate your designs to the judges and other teams. That's a really good benefit of using virtual design, so you can hide other instances and parts on your robot to only focus and select on a certain subsystem, which enhances your communication of ideas to judges. Additionally, you can see some images of some things we took pictures of and included in our portfolio to explain different parts. So you can see we hid most of the mechanisms of our robot on the left side to only show our side plates, and then some dimensions for a certain part on the right.
From designing our robot, we found that being able to simulate our motor's movement was essential to accurately know how our mechanisms will operate within our robot. This makes it easier for us as a team to know what potential flaws could go wrong and how to fix them quicker. For example, here you can see that our slides, we'll be able to simulate our slides, so we know how high our outtake will be able to go up into the backdrop. Same with our climb mechanism here. We will know how high it will be able to go to make sure it gets over the truss to hang. Additionally, Onshape offers different tools like stress and strain simulations, like you can see in the middle, which is really good for determining parts that can be under high stress and strain, so you know to enhance that location with more structural stability with other parts, etc. So benefits of CAD tools in the design process, being able to plan out the design and visually see how it's all going to work before actually making it in real life. So an example of this could potentially be if you're planning a specific mechanism that has a lot of parts that you need to order, and being a long way away from, for example, we're down in Australia, so it takes us quite a while to get parts. So if we were going to design a mechanism and we need a specific servo or piece of hardware, where you can use CAD to determine what part and the quantity of that part before we actually ship those parts over. We can also determine if it's not going to work, so we don't waste that time or that money. So it's a really good tool to use to be time efficient, considering we have a lot shorter of a competition timeline in Australia. This is a really good tool we can use to maximize our time.
CADing using math makes everything more useful and allows for accuracy. Like when you're trying to make two sides the same length, you can use the equal tool to make them exactly the same length. Whilst changing the CAD, you need to keep everything to scale, because this will actually help in your fabricating process. To help with this, there's always going to be a variety of tools that can help you, like parallel, horizontal, vertical, and midpoint. This is all going to help you in your sketches and when you're actually creating. You can see this on the images in the PowerPoint. All these tools are going to help you with fabricating, and this all, like when our nationals, we were actually complimented by saying we only need to fabricate once, and it becomes more cost efficient on all your materials.
Cool. So the engineering workflow integration CAD is a key part of engineering and FTC as in general. So how we look at it is we have CAD as the center of our workflow. So we start off by identifying the problem and challenge, and then moving to the brainstorming stage. Those ideas that get generated in the brainstorming stage then go into CAD. Those designs also go into CAD. So then from CAD, we go to building and testing. So those ideas come into real life. We then evaluate that, and then we improve those ideas back in CAD, and that cycle repeats. So this is how we integrate it into our workflow, and it's been working for us quite well.
So using CAD as a tool, it allows us to be quicker with pretty much everything. So for example, it improves our time efficiency. So we can have a whole team working on our collaborative platform that we use Onshape, and we can pretty much quadruple the time it takes to CAD our robot. And then it improves things like part ordering efficiency, so we can get those sooner. And it, as I mentioned, improves the build time efficiency. This allows us to have a lot more time to program. As we all know, that takes quite a while, and more time to test and practice for our competitions.
So beginner tips for incorporating CAD. One of this is making good use of the Rev, Go Builder, and Servo City websites. So when you go on, you can search for your specific part that you want to use in your actual robot. Often they will have a step file or engineering drawings of that part that can aid you in the modeling process of those parts. And essentially you can grab them from online into your CAD, so you can assemble your robot with your vendor parts in your assembly, which is really helpful for knowing your scales and ensuring that the parts designed in CAD are going to work in real life. So
all of these tips are extremely helpful here on the board, but I'd like to focus on just a few. Like, on the third dot point, you can see in the CAD, if an unplanned modification is made, the physical bot has to mirror what's in the CAD. This is really helpful because it helps you to show in your presentation, like, I know for our regionals, not our whole robot was identical to what our physical bot was. It wasn't identical to our CAD bot. And it always makes it so much easier when they both look the exact same, and it shows that you're so much more organized, and it, like, for later on, it makes it so much easier so you don't have to change all those other things. And like what Elliot was talking about with all the simulations, if you don't have all the proper mechanisms in there, you cannot properly simulate what you'll have to do. Now, if you look at the fourth dot point, you'll see how it talks about when laser cut /CNC cutting parts for CAD, ensure all geometry is selected from the DXF, also known as the DWG file. This is really useful as a rookie team or teams that have just started laser cutting, and to use when they start using CNC. This helps to prevent any problems when you're cutting or using any type of machinery.
I guess I'll just go through a couple more points there. So a really important thing is to try not to deviate from the CAD when assembling your robot in real life. You might have an amazing plan in CAD, but might get led down a rabbit hole when building your robot in real life. So remember to stick to your plan when you're building in real life, so you can have your consistency throughout your design process. And don't be afraid to ask for help. Utilize all the amazing resources available in the FTC community. There are a lot of people and a lot of resources that can help you. So another important point is to just keep your entire team in the loop. If you're using a software that is not collaborative, so for example, Inventor, you want to be able to have your entire team know what's going to be happening with the robot every step of the way, so they're kept in the loop with the design changes and things like that. As Dean mentioned, with your physical bot, mirroring it in the CAD, if you add like a small part on your in real life robot, that's really, really important, and you want to include that in your CAD. It's good common practice to duplicate it into your CAD to ensure that both robots are the same. Let's see.
Also, just to add on to that, Elliot, having a CAD model for a robot is also very useful because essentially what it is, it's a plan or an instructional design on how to build your robot, which say for example, once you have your final CAD and someone's been away for say 2 weeks or something, they can come back and look at that CAD and they know exactly how to build the robot and stay with the flow, essentially, making the whole process to get into practice and programming your robot a lot quicker.
So some more tips is when purchasing your parts for your design, order more than just one. Often you'll find that you'll order the parts that you need and then you realize, oh, we might need some more parts, or this one, you might accidentally damage it or break it, you might need another one. Just, it's really good what we've found that if you get one more or an extra 2 servos, you might actually need them. So that's what we recognize in our experience.
Just to add on to that, not just ordering parts, but actually like say laser cutting or CNC routing, like extra side plates, for example, because if you get hit majorly, specifically with say materials like ACM or MDF, if you get hit from the side or a corner where it may not be supported, that part may break, like what we had at our regional event, so our first competition, at one of our square beams at the back, our inner side plate, it completely snapped off, so we had no support there. So if a robot were to come to our corner, it would have broken. So those sort of things, like say if you like laser cut extra plates, that sort of thing will be very helpful and it will pay off.
That's true. If you're using Onshape, utilizing, and I think also in Fusion and Inventor they have generators for specific parts. So I know you have HDT pulley and belt generators that are available, made by the FTC community. So you can modify and make different belts and pulleys in CAD. So you can customize them from the vendor website, which is a tool that we've just been using for our development of our World's Robot. And we found it's been really, really helpful because we didn't actually have to imagine or like do all the calculations for the belt distances and everything, and the pulley teeth. We can just make like the actual model in CAD instead of having to use the information from the GoBuilder website. So so they have them for the pulleys and the belts. So on the FTC Discord, you can often find them, and also asking on there, people will have also generators for slide inserts. Just a really good tool to use if you don't want to model each individual part, like your pulleys and that.
Just to add to that quickly, so for say if you're using something like Mizumi Slides and you don't have like an account on the Mizumi website, you can simply ask, like Elliot mentioned, just ask some people on the FTC Discord, and you can see if you can get a file that way. Like that's what we had to do, and it worked quite well. So yeah, that's just the quick tip that you could probably use.
Another key thing that we brought across from the first LEGO League coming into FTC was having a design timeline. We found this especially important when using CAD, as if you have a timeline for completing different mechanisms on your robot, you can often keep track of your progress and you don't get lost in your design, especially when you have tight timelines. So having a goal of when you want to complete a certain mechanism or subsystem within your robot is a really good thing to have. Keep in mind that your final CAD part that was on your computer might be a little bit different to in real life. We've had a couple of these experiences where you might have missed a hole. Back on a dot point on the slide before, which one here? So when laser cutting CNC parts, ensure all geometry is selected. So for example, when you're projecting your CAD files for laser cutting something on your robot, you might not have selected a hole, and that can come out as a missing hole in the final product. Things like that. Or in 3D printing, if your infill is not the correct infill for your specific type of part. It might be weaker. So things like that in the manufacturing step could make your final product different to what you had in mind. So it's really important to it's really important to know what manufacturing process you're going to use to create your part. That was pretty much all we had.
Yeah. So thanks for tuning in, everyone. You can message us on our Instagram or our Facebook if you'd like some help or to gain some resources. We're more than happy to. So that's pretty much all. Thanks for listening, everyone.
Thank you
Any
very much
Q&A will be open to.
Yeah.
Thank you very much for your presentation. I hope it was very helpful and useful for those who are sitting here in the meet. And we have a couple of questions. So the first is, can you discuss the importance of accuracy and precision in CAD models when translating designs into physical robotic structures?
Yeah, sure. That's a good point. So it's really easy to get something off in CAD. For example, tolerances. Tolerances are the millimeter dimensions that could be that make parts rub together or make something a split millimeter away from not meshing gears, for example. So it's really important to, when you're designing, having more than one person go through and double check that things will work. So for example, when you're getting gears to mesh, if a hole is a couple millimeters off, your gears might not mesh in real life. So it's really important to go through and ensure that you have all your tolerances correct. So for your specific part and mechanisms within your design.
Yeah.
Is there anything else you'd like to add, Lawrence?
No, not for that one.
And one more question. What challenges do your teams commonly face when transitioning from CAD models to the physical realization of a robot, and how are these challenges addressed?
So could you repeat that? So we couldn't hear.
Yeah. What challenges do your teams commonly face when transitioning from CAD models to the physical realization of a robot, and how are these challenges addressed?
Yeah. So usually, say if we if we complete a CAD and it all works and that we simulate it, everything works, and then we go to print it, and it doesn't work in real life, then we need to go back. We need to change the tolerances, and we need to make things, say, maybe 1 millimeter bigger or 1 millimeter smaller, and make those fine adjustments, because, say, our 3D printer settings, they may have messed up because they're not perfect. And basically that process of going back and forth sometimes needs to happen if things don't work in CAD as they do in real life. And usually, because all of our team members, we have 3D printers, which is really helpful, we can maybe have 3 prints going at once, or even 4 prints going at once, so we can come with 4 options instead of just 1, to make our process of testing that quicker. Anything you want to add, Elliot?
No, not really.
So thanks for answers. And is there any questions among those who are sitting here? You can feel free to have questions. So I guess there are no more questions. So thanks a lot for your presentation. That means a lot for us that you are here presenting and sharing your experience and knowledge. So yeah, thank you a lot.
Thank you a lot. Yeah, there was very clear information, and we got the answer from our questions. So thank a lot. Thank you for supporting and being here. Yeah, we're so glad. Yeah.
Thanks.
Thank you so much for this amazing opportunity.
Thank
Thank
you.
you.
Thank you, everyone.
Bye.
Good luck.
Bye.
Good
Bye
luck.
bye.
Bye. Thank you.
And Demi.
Hey.
Yeah.
Okay. So first of all, who are we? To start this presentation, you need to understand our history and all of our implementations in the past. Firstly, Cyliis started in 2017. from the initiative of five informatics Olympics students, which had the desire to explore STEM knowledge and especially engineering. Currently, Cyliis is one of the 3 teams that's representing our high school. Alongside this, I think you have heard of them, 19044 Peppers and 2001 new team, rookie this year, Avocado Robotics. Besides from doing the robots, we like to engage with our community through different events, especially since we now have already finished around 4 to 5 big events this year regarding the STEM knowledge applied to students and even schoolers like 4th graders and 5th graders. In our team, both technical and non-technical departments are essential. They co-work together to achieve the best results in our team, especially since without a non-technical team, the technical team wouldn't be prepared enough to achieve and play in the high league as we play right now. One of the most important team values we share at Cyliis is the sustainability, especially since we put a lot of effort in creating a safe environment for the future generations to explore this project and continue it. Next slide. Okay. Cyliis structure. At the moment, we are now possessing, I think, around six mentors, two of them are international. One is from the United States, one is currently living in Netherlands. In our team structures, we possess 19 members and volunteers, which actively engage in technical and non-technical tasks. 7 of them are mostly robot-oriented task and trying to engineer as professionally as they could. 12 non-technical members which try to put all these events to reality and handle all the designs and promotional materials we post. Next, this is a photo of our team in the last league meet we had, where we had very good results. I think now Bora will explain the results we now possess.
Okay, so this league meet specifically, we won with going undefeated in all 6 matches. These are our other big results so far. So for this season, we won all of the competitions we took part in. We are currently number 1 auto OPR in the world and third just overall PR. We also got number 1 in the January top 25 for first tablet now. Last season, we had really great success with off-season events. We were semifinalists at the Maryland Tech Invitational and won the biggest invitational competition in Europe, which is the Wrestling Cup. Okay, so I'm gonna start talking about how we build our robots. So from the start of the season, we try to understand what is the most optimal way to go about building the robot. This can depend on how your competition is structured in your region and also when your competitions are. So for this season, for example, Romania changed to the league league tournament, and then nationals structure. So we decided that we wanted to get a really simple bot out as soon as possible that can do all the tasks in the game, not incredibly efficient, not very efficiently, but as good as we could in that little time we had. So for this, we analyzed what we should do. We also took really important steps into designing our robot from the start so that we could try as much stuff as we want with it. Seb is going to talk a little bit more about this later. And yeah, we settled on a few ideas that we wanted to go with for the limit spot and just went ahead and built everything. And this also gave us the chance to learn a lot about stuff we haven't tried before that we're gonna use on the next robot. Okay, so the next step is obviously moving things into CAD. After the strategy is set and most of the the broad ideas are set in stone, where our CAD team, usually one person only, takes over and thinks about how to actually package and make things work. We don't think a lot about how specific mechanisms work, only if they're very crucial to the robot's operation. Like, we didn't think that much about how the job line intake will work, because everyone had a pretty clear view of how it should be geared and just how it should work. But we all put a lot of thought into how our climbing mechanism would work, for example. We went through every detail of it to make sure that we get something that is very competitive. Okay. So this robot again, you can see it a bit more clearly that one very big thing about this is that when the design process started, we weren't sure what we should do with our optics. So our solution with this was to just leave as much space in the middle as possible so that we can test a lot of stuff. You're gonna see that our robot is pretty different from other teams this year because it has its angle slides inbuilt in the parallel plates of the drivetrain, as opposed to just in the middle of the robot. This allowed us to test multiple optic designs and also learn how to actually intake pixels side by side, which provide us with very valuable information for how we should go on about this year's challenge and just manipulating pixels in general. So yeah, okay. So this is a video for 2+5 autonomous program. This is just a showcase of how robot actually works. I'm gonna turn off the sound. So as I said, there's a drop-down intake for just easily managing the stacks and also pixels on the ground. We can adjust the height to pick up the intake from the stack as quickly as possible. And then there's just an arm that goes above the whole slice thing and then flips on the back, so just deposit pixels. And the outtake we landed with is a damper design, because we found a really innovative way to use rubber bands and micro servos to have really lightweight and very easy on the micro servos. Actually, we only broke one micro servo after switching to this, which is the whole thing that we wanted to avoid. We didn't want to break any micro servos doing this, so yeah. Okay, I think Seb is going to take it from here, talking about the iterative design process. So.
Yes. So, going to actually building and iterating parts in our robot, we take a pretty standard design on how we do that. So we basically start by. These pictures should. Oh. Okay. Okay. So we start from the CAD concepts, and we just get a few ideas. We build them in CAD. And we usually just 3D print them and test them alone. And in the end, we decide on what we want to use on our robot. So after we have our designs on the robot, we can just start testing them, improving them, and getting them better each time we print a new part. And a really important thing for iterating easy is having easy access to the 3D printed parts, or generally custom parts to make for the robot, to be able to change them very quickly. So, for example, I need to change something on the outtake. It's very easy. I just have 4 screws. I can remove the whole outtake and maybe just use a totally different concept and test that out. That's how we did in the start of the season, and it worked really well for us, as you can see. Yeah. Okay, this is the first example, and it's actually from last season on our robot. You can see the deposit for the cones. It is made out of 3 parts. The part on the left is the part with the servo. That's not really important in this picture. I'm going to talk about the other 2 parts. As you can see, the pixel will land on this part with an edge that holds it, and there's the claw that presses it against the edge. So it was really important last season to iterate that part because we found out early when we printed our first prototype. It wasn't like this. It was a really big 3D print, and it was kind of messy. We had problems with it and ended up printing it a few times, so we decided to just make it out of 2 parts and be able to change it very easy. After I did this, I think it took us, 1 day of 3D printing a few prototypes to get it perfect and to make it work perfectly. If you can go to the next slide.
Oh, yeah, sorry.
Yeah. Yeah, you can see our iteration process. So we start from this part on the left, which didn't even have the mounting holes, as you can see on the other 2. And after that, we switched to having the mounting holes, so you can just switch the parts very easy and be able to iterate much faster. I only have 3 iterations here of each part, but in reality, there are like 10 of them. But the changes between each iteration wasn't that major to show. Also, can you go back? Okay. You can also notice the claw or the ledge that catches the pixel against the 3D printed part. That also changed in geometry a little bit since the first iteration to the last iteration, and that was mostly to be able to align the game elements into the deposit perfectly and be able to transfer the cones from the claw to the outtake. Yeah. Okay, going to the second example. This is actually something we keep doing even in this season. This is a picture from last season, but it's the same concept. And I think it's really important for a team to do this, and I'll explain why in a second. So as you can see, the image, the red drawings are the string just going from the spools and are getting rerouted using some small bearings to the sliders. Why is this important for us? Well, last season and this season as well, we wanted to have the center of gravity as low as possible and in the middle of the robot as much as possible, just to have the robot perfectly and not be able to tip the robot. So at least how I went about this last season is I just placed the motors for the lift wherever I felt like it was best for the center of gravity. And then I just had the spools on a main shaft sync together with the motors. And after having the spools, I just thought and tried to draw out in CAD how I want the string routing to look. And in the end, I came up with this design which optimally routes the string to the sliders. And it's actually really cool. I don't think I've seen teams do this kind of stuff before, or at least not many teams did this before. And it's kind of a signature move for us. Yeah, okay. Now, Kenda, if you guys have questions.
So we have one question. What are the fundamental design principles that maybe rookie teams should consider when conceptualizing a new robot for competition?
I think that as a rookie team, the first most important part is seeing what kind of resources you have and see what parts are available to you and what kind of services, for example, 3D printing, do you have that? If you do, then there's a lot of stuff you can do. than just having the parts? Or can you CNC cut parts or laser cut 3D plates? If you can do that, you can think of doing more complex robots. If not, I just think about trying to use the parts I have as best as possible and make the best robot I can with the parts available. For example, as a rookie team, I wouldn't go for something as complex as what we do. I think I'd go for something simple that works reliable, have a basic autonomy, and just make the robot work as best as possible for what you have available. Do you have anything else to add, Puru?
Yes, I'd say going for just adhering to the KISS mentality as much as you can. Keep it straightforward and simple. You, honestly, especially early in the season, you should go as simple as possible with your robot. You want to get something that's working as soon as you can, just because it teaches you a lot about how the game flows and how you can just manipulate elements. That's really valuable information, and you want to use that as much as possible. There's very few ways to predict how the game is going to flow and how you're going to handle elements in your robot just by doing CAD. So getting something on the field and just working as soon as possible is very important, and keeping it simple is a great way to do that.
Yeah. I've also seen, if I can add, I've also seen some rookie teams go with the mentality that they can just start and do the most complex things they see on YouTube at other teams, but starting simple, at least based on what your knowledge is and what you can do, is very important, as Bruce said. Do you have anything else?
Yeah, I had a question about LED lighting. We see many teams use lights as a design method for their robot, but it eats a lot of battery. So do you have any suggestions on that?
We haven't experimented with LED lights yet. We are actually planning to try it this season. We got everything needed, but we haven't gotten to it yet. I've heard it also drains battery pretty fast, so honestly, I wouldn't go for it if there's any noticeable difference in how fast the battery drains. There probably is a better way to do it.
Okay, thanks.
But I do think if having LED lights, I don't know, as indicators, if you have pixels, for example, and if it helps you a lot on your robot, I just go for it. Because in the end, before a match, you're going to have a full battery anyway, so it shouldn't really matter that much.
What are some innovative design features that you have on your robot right now?
Can you go back to the picture of the robot?
Picture of the robot, okay. Do you want me to pull up that video of the latches we have? I think I have something for you.
Yeah, you can do that.
Okay. Just 1 second.
I think, if you can see the picture, I think the most important thing, and not gonna say innovative, is our really big intake. It's as wide as possible as we could get it. It really helps a lot when going for pixels, going for stacks, or going generally for any kind of element. You just go and just have to touch the elements. You don't even have to worry to align to them, and you just pick them up and go back and cycle. That's one really important thing we have.
I have to change shots. 1 second. Okay, so I'm going to share my entire screen. Okay. So I think this is pretty hard to see on the actual robot, but we have a pretty close video of this. So this is our one-way latch we use on our outtake. It lets the pixels enter the deposit box, I guess, without putting any kind of strain on the micro servos. Of course, we do still open them because it causes a very specific kind of jam that is pretty annoying. But the benefit of this is that it really puts very little strain on the micro servos. This saved so many microservers. I think we broke 3 or 4 before switching to this, and then we used it for more than a month and only broke 1. So, yeah. This is something we're really proud of on this robot. Okay, I have another video of how this works once. So you can see it's just front, back, and then the microserver can pull it forward. Okay. Just gonna switch the presentation again. No, actually it's just Q&A, never mind. Oh, wait, you wanted the presentation, right? Never mind.
Yeah.
Why is this?
I think other than the ledges Stefan just showed you, we don't really have anything else hugely innovative. We just had to keep everything simple and make it work.
Why does
Yep.
Okay.
Do you have any other questions?
If you have any questions, you can feel free to ask them.
Oh, first, okay.
Or Teams.
Oh. But I don't think I have any questions for now.
What are you going to change in your robot, like in the next days?
But we can't really leak everything, but a lot of teams know already, and I can say we are going to have an extendo. And what I can say as well is that the robot is fundamentally going to change how it works. So what you see right now and what you've seen at our team is not going to be the same in our rebuild. And it's going to be something totally different and pretty innovative, I can say. But you have to wait a little bit more for that.
Yeah. The first competition that's going to see that robot is at the beginning of March, so 8th to 10th of March.
Yep, that's when our league tournament is, and after that on 22nd March is going to be...
24th March, yeah.
22nd to the 24th March is going to be our nationals, and hopefully you can see us compete there and maybe qualify for Worlds, who knows.
So I guess there's no more questions. Thank you for your participation and for sharing knowledge. That means a lot for us. So thank you.
Thank you for your clear information.
Yeah.
Thank you for supporting us and participating here. So we wish good luck.
Thank you for inviting us.
Thanks.
It was a pleasure.
Good luck.
Bye-bye.
From Team Aries 15342 from Roseburg, they will delve into the intricate realm of game strategy and robot design integrations. So let's meet Team Aries, and you can start if you're ready now. Thank you.
All right, sounds good. Yeah, so hey guys, my name is Elias Malik. Like she said, we are Team Aries from Roseburg, Oregon, so on the western side of the U.S. Last season, we made it to the World Championships and won the third place design award for the Jemison division. So our goal today is basically to share some of our design philosophies and talk about how one might go about doing well this season. So let's get right into it. I'm going to share my screen here. All right.
Yeah, we see the screen.
Perfect. So the first thing that I'd like to talk about is the engineering and design process. So especially when you're trying to go for a design award during a tournament, you really want to focus on having some sort of design process that you're telling the judges about. It doesn't have to look exactly like this, but this is one of the more common ones. You ask to identify the need and constraints, you research the Imagine possible solutions, plan by selecting a promising solution, then you create a prototype and then test it, and then improve and redesign as needed based off that testing. So we'll go through a few examples of how this might be done. So when you're asking, you want to think about like, what problems are you trying to solve, right? This year, maybe you're trying to come up with an intake, right? So you need to pick up 2 pixels. So the question is, how do you pick up 2 pixels? And then you can identify constraints in the next section. But you need to think about things like time, your budget, what parts you have to work with. Are you only working with GoBuilda or only Rev parts? Things like that are really important. Your research. Have other people solved this problem before? Is there anything that you can learn from just looking at YouTube videos, right? Because a lot of the times you don't have to reinvent the wheel, right? If somebody already has a really good intake, you can think about using something similar to it, right? It's very common with like the example of the claw from Team 16379 Cookie Bots, right? Many people decided to go with the 2 claw side-by-side setup, right? So that's a solution that worked and people just started using it. So that's a good example of doing your research. Our example of this was when we were doing a design matrix where we had a few different sorts of mechanisms that we were ranking, and we gave them criteria like speed, reliability, simplicity, etc. And then we gave each one a score from 1 to 10. And that's how we made our decision here in the end on which design we would ultimately end up going for. So a decision matrix like this can help you simplify your decision making. So the next step is to imagine and plan, right? So what is the best case scenario and what is actually possible? So set goals, right? So one of the first things we did, which I'll talk about a bit later, was set times for how long we wanted to be intaking, how long we wanted to be driving, and how long we wanted to be outtaking, right? So setting goals like that allows you to not just say, oh, the intake looks good enough. It lets you think, does it meet our goal or does it not? If it doesn't meet our goal, it's not good enough, right? So it's important to make sure you're setting goals like this. And this was our robot from last season. So, and it's also important to make sure that you're doing sketches because the judges love to see sketches in your portfolio. Create and prototyping, right? So it's important to remember that when you're making your intake, you should not be trying to CNC a whole new intake system when you haven't tested it at all yet, right? Make sure you're testing it out. One of the things we like to do is 3D print because it's quick for us, but you can also use cardboard. We do a lot of cardboard prototypes. Zip ties and duct tape are our favorite prototyping tools. They're meant to be rough, right? So later you'll come back and CNC it, or maybe you'll use some better parts from GoBuilda or whatever. But if you try to finalize the first time around, you're going to run into a lot of speed problems. You're not going to get out the proper design as fast as you could if you were just prototyping. So testing, right? What works and what doesn't and what could be improved, right? So for collecting data, we went with, it's kind of hard to see, but these are our clamps for our linear slides that we made that are custom. And it's holding on to this belt. Right, on the inside of the clamp, there's some teeth that are holding onto the belt. And the problem before was that it wasn't very rigid, right? So if you pulled on the belt, it came out here with our load scale that we used to measure. It came out in 8.12 pounds before it snapped out of the belt. Out of the clamp. Whereas when we changed the design a little bit to make it a little bit more rigid, it was able to withstand 39 pounds. Right, which is a significant difference for only a small bit of change of the print geometry. So collecting data is really important because it meant the difference between having a lift that functions well but breaks a lot versus one that hasn't broken the entire season and we still use to this day. So it's important to think about that. Improve. How are we going to improve? So that, again, goes back to the data that you were collecting in the previous step, right? How do you go from a simple 24-hour challenge robot or whatever it might be, your first robot, to your finalized robot that you end up taking to Worlds or State or whatever is your max competition? So it's important to make sure that you're using that data to make informed decisions. Say, oh, our intake is taking a second to intake, but we want it to take half a second. Maybe we need to use a faster motor. Maybe we need to use a counter roller. Maybe we need to use something like that, right? So just think about that. So now we're going to transition a little bit to how we went about this year's game and all that it entailed. So, like I was saying before with the goal setting, when we were at our kickoff, the first thing we did as a team was calculate the max amount of points that you could score, right? If you focused on just one robot on the field, right? Let's say you're on the blue lines. If you picked up all of your blue alliance pixels in autonomous, you place the purple pixel, you place the yellow pixel, and then you maximize all of the pixels you have during teleop in your wing station, how many points does that give you? And I think we ended up with something like 435 points or something, but it's pretty high up there. So what we found was that in order to accomplish that max score, we needed to have 3-second cycles. So we wanted to go from the backdrop to the wing and back in 3 seconds. So what that allowed us to do was dictate, what sorts of drives can we use? Are we doing a fast drive that can go straight through the middle that's short? Do we go through this side where there might be a little bit less traffic congestion to accessing the wing? It's a lot of different variables, but it helped us narrow some of our options down. So I highly encourage you to set goals like that. For example, on our intake, we set constraints like, well, it must be able to hold 2 pixels, and it can only hold 2. Right? If you hold 3, now you have penalties. If you hold 1, then you're not being efficient with your time, right? So it has to be 2 pixels. You need to have a way to pick up from the stack. And the stack is proving to be pretty difficult to do reliably for most teams right now, but it's important to make sure that your intake can pick up from the stack. You need to make sure that we can't take more than 0.2 seconds to intake. That was the goal that we set because of our 3-second cycle goal, but it could be whatever your goal might be. It must use sensors to detect when to our intake, because oftentimes when it's all the way in the wing, we can't see as the drivers, right? We can't see if we've intake 2 exactly, and we don't want to incur penalties. So using sensors is a must. So next what we did was we looked at what some of the other teams were doing, right? So we spent about 2 hours sketching intake ideas on the board. So we looked online, seeing YouTube videos, and there wasn't much at the time because this was really early season, but we just looked to get some of the ideas. And we saw people had claws. We saw some people start to do active intakes, but we started to just draw on the board for 2 hours, right? And we just kept drawing different ideas and labeling them. And in the end, we decided to rank them and decide on 3 that we were going to pursue and try to prototype and see which one works best. But it was really important to draw for 2 hours nonstop, because there's a big design philosophy, which I'll show this video because he explains it really well. But basically, your first ideas are never going to be your good ideas. You have to get through your bad ideas in order to get to the best ideas, and that takes hours of time. So we're going to watch this quick video about it. So you can see that was a great explanation of what I'm talking about, right? A lot of people went with, at the beginning of the season, they said, oh, let's just do a claw, right? Which is great, and it works. But is it the fastest thing you can do this season? Up for debate, right? I've seen some claws that are as fast as an active intake. I've seen some active intakes that are slower than claws. It all depends on your implementation, but it really depends on how well you designed and prototyped at the beginning and brainstormed. So we selected a few ideas we liked and we prototyped them. So to test our spinner ideas, we decided to attach a drill, some zip ties, and some surgical tubing, somewhat like this. This is on a motor, but you get the idea. And we just held it, right? We just held it in the air, tried to intake, right, to see what it would do. And we just tried to see what worked, what doesn't, right? Does this work on the stacks? Does it not, right? Can we intake 2 at a time? Things like that are really important. So next, I'd like to talk a little bit about some constructability, operability, and maintainability. So these are some of our main design philosophies that we focus on whenever we're coming up with any design ideas. And we'll go through some examples of what each one means and how it's used in FTC. And these are things that is used in the industry every day. So it is a very valid and important idea in engineering. So the first step is constructability. One example of this is embedding nuts in your prints, right? So instead of using a set of pliers to hold onto the nut and then a screwdriver to tighten up the screw, you can just set the hex nut inside the hole that the 3D print already has, and that allows you to just be able to tighten without any need for pliers on the other side, which is really helpful because now it's easier to get into places, right? You're able to build the robot faster because you don't need to have 2 different tools on at the same time, right? So this is something that we've really benefited from, and we've put embedded nuts on almost all of our parts now that we 3D print. The other thing is we recommend about 0.1 to 0.15 millimeter tolerances when embedding into PLA. So if you guys are looking to try to do something like that, we recommend about 0.1 to 0.15 millimeter tolerance greater than what your nut is. So this is an example of our embedding of the nuts into our 3D prints, right? We have this hole here set aside for the hex nut, and that allows it to stay in place and allows to tighten the screw without needing to put pliers on the other side. So again, it's the easy assembly and construction of the robot to make building it as fast as possible. All right, so operability. So reliable mechanisms and stress tests. So think about these questions when you're brainstorming a mechanism. If you were to run it 10 times in a row, will it ever fail, right? This is especially important with transfers, right? Will it work every single time, or will it just work 3 times in a row and then the 4th time it'll get stuck inside your robot, right? We had problems with that as a team, and we had to work on figuring out a way to fix that, right? So if the pixel comes in diagonal rather than straight into the intake, is it still going to work, or is it going to fail? If the robot hits us in autonomous, can the robot still recover and score, right? These questions are all stemming from the reliability aspect that you can see here. So it's really important to make sure that your designs are operable. That's what that means. So, for example, the properties of a system which make it work well in production is the definition. So we did a hex socket twister last year where instead of having to reprogram the servo for our twister mechanism on our claw, we were able to just rotate this this part right here, this embedded section, into our attachment. So our hex socket twister was able to align without the need for reprogramming a servo. So that made building it faster, that made programming it faster, because now we didn't have to reprogram the servo. We could just start working on the robot. So that was really helpful. Maintainability, right? This is probably one of the most important things you can take away from this, is if you had to remove any part in order to access a screw, then it's not easily maintainable, right? If you were to have this drive system that we had originally, this was from a few years back, we were planning on doing this gearbox drivetrain where the motors were all inside the drive here, right? Instead of sticking out the back. The problem was we had issues with accessing our screws, right? All of these screws on the wheels, all the screws in the motors, everything was all tucked away, right? We couldn't access it. So we'd have to remove the front plates in order to access any of the screws that we needed from the wheels, which is not good. More recently, this is some of our more recent designs, we have access holes here, we have access holes here, right, everywhere to make sure that we can access everything that goes on inside of this gearbox that we have, right? So it's important to make sure that you can access everything. And one of the better examples of this is on last year's robot when we had a bunch of different screws here. And you can see all the screw heads, and all of these had to be maintained, right? Just in a competition, some of the screws will come loose. You have to be able to maintain them properly. So one of the best ways we did that was just by making sure all of the screws faced outward, right? So if you ever needed to tighten anything, it was all available to you from the outside of the robot. Nothing was removed, no wires were in the way. everything was easily maintainable. It was easy to repair something if it broke. That's really important. So continuing on about standardizing some of these designs. So it's a bit of a transition, but it has to do with that idea of maintainability, right? Making sure you can easily maintain parts. And it's easier to do that when your designs are standardized. This is one of our wheel pods that we've been using last year and this year. And one of the things that we had this 3D print here where we wanted to hold on to the hex nuts to stop this Rex shaft from spinning because we're using a dead axle design. So we wanted to make sure the Rex shaft didn't spin so that the screws would stay tight. And so on this side, you'll notice that we have this pulley, right? And we can't move the hex nuts in, otherwise they'll intersect with the pulley, and we don't want that, right? On the other side, though, you don't have this constraint. You don't have a pulley here, right? So naturally, one might think, okay, just make it a smaller print, right? Less plastic, you get the same job done. Well, we decided not to do with that because what you can do is use the same exact part as you did for the front side where we had the pulley and that constraint there, and just put it on the back because it doesn't hurt anything to keep it the same size. But now what it allows us to do is only take one replacement part to a competition. Rather than worrying about both the small black piece and a large black piece, now we just worry about the one big black piece and we can make multiple of them, right? And replace them whenever needed. So it's important to think about that when you're trying to design something. Make sure everything is kept as standardized as possible. So now we're going to talk a little bit about some of that prototyping and the ideas of making a finalized product with 3D printing and other materials. So with material science, we looked into some ideas on what sorts of print material we wanted to use. Did we want to use PLA, PETG, ASA? There's a lot of different options, and it kind of depends on what you have available. But one of the main things we looked into was PLA, PETG, and ASA. So what we found was that PLA, under this load test here, which was available by CNC Kitchen on YouTube, it's a great YouTube channel on 3D printing. When you pull on this hook here, it broke under 161 pounds. And you'll see that here when it's reflected in the maximum force. You'll see that PLA performed the highest out of PETG and ASA. And the good thing about PLA is you'll notice that the hook is sort of flexing under this load that it has, right? Has a lot of load on it. And it's just flexing rather than snapping. That's really important. And the good thing is it's really easy to print, right? A lot of printers are meant for printing PLA. So it makes it ideal for most of the FTC use cases. And over 70% of our robot was 3D printed using PLA. I mean, you can see most of them, but I'll point them out. Like this was all PLA. Our battery case was PLA. All of these parts for our lift was PLA. All of this was all PLA, right? Even our grabber, all of that. And during this robot iteration, we had 0 breaks of any parts, no snaps, no nothing, throughout all of the world championships, the three scrimmages that we did, hundreds of hours of drive practice we did prior to all of those things, and countless autonomous fails and collisions where other robots rammed into us at full speed. It hasn't broken a single time. So a lot of people in our league try to argue, or in other leagues as well, some say that, 3D prints are brittle, right? You can break them easily. It depends on how you're using them, right? For example, we could have made a custom 3D printed drivetrain, for example. But drives usually get hit the most by other robots. So instead of doing that, we decided to go with making 50-52 aluminum plates, because we could have printed it, but the drive gets very beat up. So we had the worry of it snapping or breaking in a competition. We'd have to replace it. And that's time that we really don't have in the middle of a competition. So that's about it. Love to have any questions answered, and good luck to all you teams.
Thank you for your presentation. It was really good, and it was really clear for us. But I have some questions. So the first question is, where there any unexpected situations during the competition that required on-the-spot adjustment to your game strategy or your robot design?
Yeah, so I'll give a few examples. One of the more recent ones is, for example, our transfer. When we were first working on it, we had issues with sometimes the pixels would fall out of our intake, right? So our transfer and intake are connected to each other. So our intake flips up, and sometimes the pixel would come out of that intake. And it was mid-competition that actually happened when we were in a match. And so we had to figure out a way to just drive without having the ability to have two pixels in at once, right? Because we already have a pixel stuck on our robot now. So it's really important to make sure that you're practicing driving with these situations. Luckily, we had this happen in practice before. So we use things like putting tape on our drive to make it a smooth surface. So if a pixel did fall on, it would be able to shake off if we just drove forward and backward a little bit. Things like that are really important to make sure that your robot is reliable and driving as best as it can for a competition.
Okay, thank you. And can you discuss any innovative solutions or like unique approaches your team took in integrating game strategy in this season or in the last seasons? Any?
Sure. Yeah, one of our more innovative mechanisms was our passive lifting mechanism that we did this year. Unfortunately, I don't have any pictures of it on this presentation. But the idea was that we were maximizing all of our 8 motors. So we didn't have any motors to use on our lift mechanism. But the other thing we were considering is that when we were doing that original goal planning at the beginning of the season, where we had that 3-second cycle goal, we were planning out goals for how long we wanted to take to hang. What we noticed was that a lot of the teams who were using things like a linear slide or linear actuator, right, a lead screw powered actuator, we found that it wasn't as fast as if you just used a passive hanging mechanism, right? Because with a passive hanging mechanism, you're able to just drive forward, immediately go onto the rigging. So it's important to make sure that you're looking into your goals, because again, after planning out for 2 hours of drawing and coming up with ideas, you start coming up with the best ideas you can. And we never stopped coming up with ideas. I mean, we're still trying to think of ideas every day on how to improve, how to get better, and accomplish that 3-second cycle goal. So I'd say our most innovative mechanism was our hanging this year because it's passive. But there are many different solutions for the hang, and this is just the one that worked best for us.
Okay. And what's your ultimate winning strategy?
Like in a match?
Yes. What kind of robot in your alliance you'd like to have to win the game? Like.
Yes. So that's something we've been thinking about a lot because our qualifier is coming up soon. One of the things we've been mainly looking into is someone who can feed pixels to us. So our robot has an extension on both horizontal and our lift. So we can access some of the pixels that some of the other teams can't. But having a team that can go grab pixels from the stack especially, and then bring them right in front of our robot while we sit on the backdrop and just keep scoring, proved to be really reliable and really quick at the last tournament. So we were reaching some of those 3-second cycle goals at the last tournament, but it was only for the ones that were brought to us, right? The pixels that were brought right in front of us. So we're looking to improve that. But the main point is that having a team that can bring pixels right in front of us is really important to allowing us to score our highest because it minimizes our driving time, right? We can just sit in one spot and just keep scoring.
Okay, thank you. Is there any questions from the audience? У вас есть вопросы какие-то?
What's your favorite season in terms of maybe robot design? What's the season when you have the best robot design in your opinion?
I would have to say this season is probably our best robot design. Mainly because this is, like, for example, for me, this is my 7th year, sorry. 7th year in FTC. So I've been doing it a long time, and a lot of our teammates have now become fairly senior in FTC as well, so they've become pretty experienced. So it's just been more natural to us to be designing pretty innovative solutions to the different problems we've had, whereas we could have gone with something simpler for our robot. We decided to go with something a little bit more complex and push our limits to see what we could actually accomplish. And it's proved to be pretty good this season, and we're, like I said before, we're actively improving. And I think this season has a lot of room for growth in actively improving. So I encourage a lot of the teams to just try to keep thinking of ideas. Right? How do you make it faster? How do you design something even better, even when you think it's done? Because there's always room for improvement.
Yeah, we definitely agree with you. So thank you for your participation. I think there are no questions. It was really clear and interesting to listen to you guys. So it was the team Aries 15342 from Roseburg. So thank you for coming. It means a lot to us. So yeah.
All right. Thanks so much.
Yeah. Goodbye.
Bye.
Hello guys, thank you so much for inviting us. We are the BraveBots team from Romania. We are going to share our screen now because we have also prepared the presentation for you. Okay. Please tell us if you can see our screen.
Yeah, we can see it.
So, we can start. In our team, we have 14 members, 8 volunteers, 4 mentors, and we have been participating in the first competition for 8 years. And that means that we have been part of FTC ever since it came into Romania. We are most proud of the award that we won last year during the national competition. We got Connect 1 for outreach, and working with our contact is between 18 and 24 years old. So that means that a lot of young people are really interested in this first and STEAM area. App to the whole first community. So now, even if you are not part of a Romanian team, if you are an international team, you can still register and use this site. Through all of the events that we have planned this year, we were seeking to really embrace this motto.
Little Brave is our FLL Challenge team. With the help of 2 NGOs, we formed this team.
We built from scratch 60 physics experiments and 45 chemistry experiments. They are educational materials that we donated to schools because most of our middle schools in the county don't really have the chances to a great education. And so rather than spending a lot of money on these materials, we chose to donate them to them. The next event is called Robotica. We held it with the help of the university in our city. And that way we formed a partnership of 4 years with them, so that many more students from high school in our city would be willing to actually go to university in our city home. Then another event, also in a partnership with another university in our capital city of Romania, Bucharest, the Polytechnic, which was called Mechatronics, and united 20 teams, 20 FTC teams of our country. Next, we have Brave Around the World, which is a podcast we started a year ago, and actually this is the way we met the Bolt M3 team. Next, we have Brave to the Rescue. We wanted to get in connection with the rookies teams in our country, and that way help them from our experience, help them start this journey first and really promote its values. Another project we started this year was RoboHub Academy, which is actually the first hub, the first robotics hub in our county, which is an open space for any young minds. And we also formed a lasting friendship with another team from our country, Titans, and that way we held our first league meet, which was called On Stage, this year.
That is all that we have prepared for you today. If you want to check more of our events or more of our weekly. Now, if you have any more questions for us, in case we haven't covered something.
We had a couple of questions. So, what strategies do you employ to ensure inclusivity and accessibility in your outreach efforts?
So, about the inclusivity part, for example, this year we formed connections with more than 60 schools in our county, and among these, it's also included a educational inclusive center with children that can't go to, let's say, the usual schools and have like special needs educational requirements. And we try to make their classes more fun and try to teach them something from science, something from STEAM. And actually, we had a surprise. Some of them didn't even touch a laptop in their lives. So when we went to them with Lego sets, interactive Lego sets, and coding, like fun coding games on our laptops, they were very excited to learn all about that.
Cool. Thank you, BraveBots, a lot. That really means a lot for a team and hopefully to other Kazakhstani teams.
Thanks so much for having us again. And we hope that we will further collaborate in the future because I think that this could be a really nice international friendship.
Thank you, guys.
Thank you.
Thank you.
The next
Bye.
Bye.